Okay, today we're going to start on chapter 14. That is on fluids and elasticity. We're mainly going to study fluids in chapter 14. It's hard to teach this just on a whiteboard. I don't have anything to demo with, and it's really hard to demo in the barn some of the things I would want to with fluids and the equipment. And hard for you guys to see on a video what I'm trying to accomplish. Even if I had a bucket full of water and did things and stuff. So what I'm going to do is I'm going to go over it, talk about it. I'm going to try to give you a video to watch along with the lecture. And so you'll do about a 1 page or so of notes on that. I'll put it in the Canvas instructions along with this. So you'll get hopefully a decent understanding of me and the video that goes along with this. So kind of want to start out there. Now fluids is a little different. It's chapter 14, fluids and electricity. So before we talk about what a fluid is, fluids, in liquids, I'll say are liquids and gases. Gases can act like a fluid as well. Fluid just means substances that flow. Most of the time, these substances that flow, we're going to assume they are incompressible. We're going to assume you can't compress them into a smaller amount of volume. They're going to take up the same volume all the time. Of course, if you took like a junior level fluids course, there's compressible and incompressible flow. Compressible flow is much more difficult mathematically, of course, than incompressible flow. The models for it are. But we're going to assume that a fluid is an object that flows, doesn't compress. It can be a liquid or a gas. Okay. One other thing fluids do. Fluids exert pressure. Now, the problem is, I haven't talked about what pressure is, so probably I need to do that pretty quick. But before we do that, I do want to talk about things with fluids we talked about. If it's incompressible, with fluids, density is a valued quantity. To understand how fluids work, we need to understand the density. You guys know the density of water. Water is pretty heavy. You carry a gallon of water. You ever try to pick up a 20-gallon aquarium? I mean, that would be... I've got a 50-gallon aquarium. My gosh. I had a whole house, actually, where I had a 50-gallon aquarium. And when we moved out of it, you could actually see where the floor at the old house had gave in a little bit from it. From the wall, because it was up near a wall, where the 50-gallon tank was. And based on the density of water, which we'll say here, it says about 1,000 kilograms per cubic meter. So think about it, a cubic meter, 1 meter by 1 meter by 1 meter. A cubic meter of water would weigh 1,000 kilograms. 2,200 pounds. It's a lot. When I was a kid, in 70s, 80s, early 90s, a lot of people had water beds. And before you had a water bed, you had to make sure you had a strong enough floor for a water bed. People that lived in trailers, especially ones back, in the 80s and stuff, 80s and 90s, they weren't as strong as some of the newer ones are. They weren't as well built. If you lived in a trailer and had a water bed, you were setting yourself up for a bad event to occur. There were tales of people's floor giving out because over time, just people being asleep and the floor crashes down underneath them a little bit. It's visualize it is kind of funny. Of course, if it's happened to you, it's not funny. But water is a very dense material. If you had to carry water, going on a long hike, and say you're carrying a bunch of water bottles in you on your pack, it gets heavy over time, pretty quick. Of course, air isn't as dense, but air has a weight, and hot air balloons work based on that. They have a certain density of them as well. But let's talk about what density means. So we need to talk about what density means. Density, we're going to use rho for density, and it's a Greek letter rho. And really, this is going to be mass or weight density. And with density, we're normally thinking how much stuff is in a volume. Stuff in a certain volume. When you're thinking of a density, now that could be people density, how many people are in a building. That could be cockroach density. If you've got cockroaches, my gosh, I got 5 cockroaches per room. I was infested. I got 500 cockroaches per room. Oh my goodness, and they'd be all in the house and stuff. We don't want that. But that's density. How much of something is in a volume. Now, with fluids, like I said, mass or weight density, and we're going to say that's mass over a volume. And that's for mass density. Weight density would be the weight, which is the force of gravity over the volume. Okay? So mass or weight density. And just to give you an example, like I say, water is about 1,000 kilograms per cubic meter. Air, a cubic meter of air, if you had a box a little bit bigger than a yard, 3 foot by 3 foot by 3 foot high box, that would have a weight of about 1.2 kilograms. That'd be about 2.5 pounds. Yeah, 2.5 pounds. So those are some values for density. Density we're going to use, be able to calculate the density. The thing about density, it's why it's such an important note. Density, let me see if I can write this, is a material property. For water, at certain temperature and a certain pressure, it's going to have a certain density. Air at a certain density and a certain pressure will have a certain density. So it's something we can use to help us figure things out, because if I got water, I know I've got this much of it. If I've got mercury, very heavy liquid, much more dense than water, I know based on a weight or a volume, I can find the other one because I know what the density is. That's what it allows you to do. Now we talked about pressure, and let's look at 14.2, because 14.2 deals with pressure. You might have heard the old Queen song, Under Pressure. I thought there's a line in that song, under pressure, pushing down on me, pushing down on you. And I thought, wow, that's actually pretty good. Now, as you do know, I think one of the guys for Queen is a physicist or a cosmologist, one of the two. He's basically a big science nerd, so maybe they use that when they're writing. With the amount of substances they were including, I don't know about that. But it just happened to be that pushing on something, I push on this board, I'm exerting pressure on it. Air has a certain pressure on us because it's pushing down on us. If you go underwater, your ears will pop. If you're diving, or if you go up above a certain altitude because of the pressure on it. That's when you want to think of pressure. Pressure, it's push on an object over an area. Push on an object over an area. Now, let me see if I can demonstrate. I do have something I can demonstrate this with. My loppers. Right? I'm using these out in the yard a little bit. Now, if I hit myself, hurts a little bit, right? Hurts a little bit. Those are real. Hurts a little bit on me. Now, question is, what if I put my finger right here? Whap. This will lop stuff. Let me see if I can find something to lop around here. Let me see. I'm still looking. This isn't very. I can lop a straw. Well, I can try. It didn't work too good. What if I. Here's an old power supply I had dank left. Just happen to have nearby. And I can use this. It can be hard to cut them otherwise, but. There we go. Oh, that's a big one. They're dull because I've been cutting with them so much. But it works. Cut by, especially the big one I cut. Okay. Now, how did this cut it? I got a bunch of old computer stuff I'm going to take and recycle. Make $20, $30. How do scissors cut? How is this? I stab you in the eye. No, I wouldn't stab you in the eye. Stab you anywhere. How does that cut people? Ouch, ouch, ouch. Pressure. Say pressure, and I say, yeah. Because if the blunt end here, it doesn't hurt much, right? I put a force, it's spread out over that area. Now let's take the same force, put it over this little area. Ouch. It hurt is hard, it still hurt. Ouch. That hurt. Why? Look at that. Same force, much area, smaller area. I had a lot more pressure on me. Scissors work. Dull scissors have more area. If I use a little wet rock or a sharpener and get these things sharp, they cut real good. Why? Less area, so the same force is able to make the object yield or go through an object because it can exert more pressure on it. Take the cat over there. What are you doing, Chloe? Come here, girl. So, come here, Chloe. Kiki. I'm going to show you something about her. Chloe. Come in here. Chloe, come here. Come here, girl. All right. This is Chloe. You've seen her before. She's a good girl. Yeah, you like the daddy. Okay. But Chloe has teeth. Ouch, ouch. Her claw got me. Won't show her teeth. How could her claw get me? Why is her claw so sharp? Ouch, sorry. You go. Ouch, ouch, ouch. Okay, you be nice. How does her claw get me? It's so small on the ends. It's so small, so just a little bit of push, if she had her claws out, would hurt me. It would grab, it would puncture my skin because of the pressure on it. I can only hold up to so much pressure. My skin can. If it's blunt, doesn't do anything. You know, it's her paw, it's blunt. But her claws, her teeth, sharp teeth, small area, large force, lots of pressure. That's how they puncture. How you get puncture wounds. Okay? You do good, Chloe. All right, here you go, girl. All right. So I've kind of let the cat out of the bag, you could say, about how to calculate pressure. So pressure we're going to say is force on an object over the area. When the force goes up, the pressure goes up. Make sense? When the area goes down, make that knife sharper. Claws versus a paw, pressure goes up. So area has to be a reciprocal relationship. So when this one gets bigger, pressure gets smaller. And that makes sense. And also when this gets smaller, because it's underneath, pressure gets bigger. They're inversely related to each other. Okay? Now I will say here, the force needs to be perpendicular to the surface. And if it's at an angle to the surface, say this is your surface here, the force comes in, only the component perpendicular, this force perpendicular to the surface, does the pressure. Does the pressure. That, in case you have a question about that. Now, pressure units. Well, here it's going to have a newtons per square meter because forces in newtons, area would be in square meters or square feet or something like that. In SI units, we use square meters. And we basically call this a PA, which is a Pascal. Blaise Pascal did some work on this. Actually a great mathematician as well. 17th century mathematician. One of the first to study fluids. Okay, that's a pretty small unit. Actually, a newton. Think about 1 newton. A quarter pounder of force over a huge, a square meter, 1 meter square. So lots of times, kPa, which is 1,000 pascals, is often used. That's 1,000 newtons of push, which is about 255 pounds, if I'm not mistaken, over 1 square meter. All right. Now, cause of pressure. Anything that exerts a force on it, I'll just say forces, but in particular, gravity pushing down, and I'm going to call this a hat of fluid. Okay? And it could be, I'll just call that a hat of fluid, and I'll explain that in a minute. And thermal. So in thermal interaction, things get hotter. They exert more pressure on things because more molecular collisions with a surface. So if things get hotter, remember we talk about heat and temperature is just basically vibration. It's how often how it's the temperature measures how much an object is vibrating. Okay, that's all temperature really does. So if an atom's vibrating around more, if it's hotter, it's going to vibrate around a lot more. So it's going to hit the sides of a wall more. If it hits the sides of a wall of something more, it's got more pressure. So how do you have that happen? You have temperature go up. You can have more material, like stick more helium inside a balloon that can only get so big and increase the pressure that way. Gravity pushing down. When I say hat of fluid, we have air pressure around us, right? How do I know we have air pressure? You've seen there's a thing with the old Magnenberg spheres. You basically, you put 2 pieces of glass on top of each other and you push them down really good, kind of ring them, they call it. And you can't really pull a piece of glass off the other one. You have to kind of slide it off and pry it up because there's no air in between it now. Once there's no air, you've got all the air up above it to space pushing down on it. And how much is that? Actually, over 1 inch, 1 square inch, that's 14.7 pounds. at sea level, where we're at, maybe 14 pounds. So, I mean, that's a lot. So a piece of glass, say this big, that's a lot of square inches. Say, 10 by 10 would be 100 square inches. 100 times 14, that's 1,400 pounds. Yeah, you can't lift up 1,400 pounds off that piece of glass. The pressure is doing it. Now, if you pry it a little bit, air gets underneath, so now the pressure down and the pressure up kind of equalize each other. And then it's like, it's just the weight we worry about. A hat of fluid on your head up to space. It's on top of us. I'm wearing a hat of air right now. And everywhere I go, there's a hat of air walking. Now, the same ones that walk with me, I walk through it, but I've got the same hat of air. If I go up in elevation, I have less length of my hat, on my top hat, and so there's less pressure on me. But that hat of fluid on top of me is what causes pressure on me. If it's pushing on me at about 14 pounds. And if my body wasn't pushing back, I would shrink them up like this. But you may have seen, aluminum cans, take the air, get them, put a little water in the bottom and get the water boiling. So you got the air inside's got low pressure and steam's coming out. If you quickly cool them down, air pressure, you cool it down. Now that air that's real hot goes cold. Dunk it in water real quick. What will happen is it will actually crinkle that can. When I was teaching high school, I thought, we're going to do it in a 35-gallon drum. Well, what I did was I did the same experiment. I took some, the kid brought in a 35-gallon drum. We put that much water in the bottom, used Bunsen burners, heated up really good, had steam coming out the top of it. Then we closed it off, and I sprayed down the outside of it, got it sealed so no air could get in. And so there was a lot of hot air, and it was hot air, it was rising, so there was effectively less of it in there. As it cooled down, the molecular collisions on the side were less. And when they were less on those sides, there was less pressure inside. Now, a 55-gallon drum, it's pretty strong. But at 14 pounds for every square inch on this big 55-gallon drum, that's a lot of square inches. So I figured there was enough pressure to pop it in. And we did that. We closed it, sprayed it down, put ice on the top, had a student help me. It was on a teacher work day. And before we had video cameras like we do now, we videoed a little bit with some, one of those video cameras, but it didn't break. I was like, crap. And I told the student, I said, just watch it, make sure nothing happens. So I walked out, went 2 doors down. I was teaching high school at the time. Went down to the teacher's lobby where, teachers were at. I guess they were supposed to be working, but for some reason they were there. And I was sitting there with them, and it was break time or something, I don't know. And they was like, what are you doing, Doug? I said, who are you in there? I said, I explained it to them, and they just kind of rolled their eyes. It's normal night stuff, right? And so I'm sitting there. Dang it, I'm frustrated, blah, 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 blah. Didn't work. Next thing, 10, 15 minutes, pow! It was like a gunshot going off. They were like, what was that? What was that? And I was like, it worked. It worked. It was a eureka almost moment. And I was like, hot dang. And I took off running in there. And I got in my lab room. And the guy was in there. It's like, night, it worked. Look at this. It crushed 55-gallon drum like that. Outside air pressure, because I'd sealed off the top of it. And heated it up. Heating it up made the air inside, there was less air in there because it kept hitting the sides more. Steam was coming out. Closed it off, cooled it down, less air inside than out, got it cold. The pressure difference was finally enough once it cooled down a lot to crush the 55-gallon drum. So when I was teaching back in high school the next year or so, I would teach that a concept, and I'd crush the little aluminum cans and stuff. And it's a cool little experiment. And then I said, you think this works with 55-gallon drum? And, oh, no. I said, well, how do you explain this? And I'd roll it out of the back, and they're like, whoa. But, it's trying to have a little fun and explain it. But that hat of air all around us is pushing it. It's pushing in here. It's pushing on my legs, pushing on my eyes. if you ever saw the movie with Arnold, when he goes to Mars and tries to set up the settlement and stuff, Total Recall, at the end of it, they're out there on the Martian atmosphere. Well, Mars has a very low atmosphere. And so what would it do to a person? Well, to offset the air pressure, we push out. So, his eyes start bugging out, his body starts inflating out and stuff. And of course, then the things from the aliens start creating enough air pressure, and he goes back in, he doesn't die. But, it's air pressure's interesting. One of the Russians actually coming in during re-entry, the capsule depressurized, and they weren't wearing a spacesuit coming in. And without wearing a spacesuit and depressurized the capsule, think about what happened out of his orifices and out of things where the body would push out because he lost all air pressure. His body pushed everything out. Of course, he suffocated, but he also, everything kind of bit nasty. All right. Causes of air pressure. Chloe, you're on my book, young lady. Okay. All right. Now, I talked a little bit about atmospheric pressure, what causes it. Erase a little bit here. Okay. And talk a little bit more about that. Let me get a little bit of acetone here. Now, one atmosphere is 101.3 kilopascals, which is about 14.7 pounds per square inch. I also include that because you may have heard that before. Kilopascals, probably not. That just gives you an idea of the conversion factor between them. Now, in liquids, I said it's a function of how much air is on top of you. In a liquid, it's a fairly easy calculation. Most of the liquids we deal with are water. But as long as if it's a homogeneous liquid, it's the same material all the way through. What you do is just the pressure in a liquid. It's just the atmospheric pressure, and this is a P, not a rho, plus the atmospheric, because that's what's pushing down as well. And the further down you go, of course, you got more pressure on you. You know that. If you do any diving or something off a high dive, you understand that a little bit too. Skin divers can only go down, 60, 70, 80 feet. Because the pressure becomes too much on our ears and everything. You have to wear specialized suits the further down you go. At the bottom of the ocean, do you have giant creatures? Well, if you do, they're going to be gelatinous. Why are they going to be gelatinous? Well, they're going to have to deal with all the pressure above them. If they change, I just use from altitude, but if they change depths underwater, the pressure change is going to be a lot. Some whales dive down and eat giant squid. When they dive down, they get collapsed in a lot. And on the way up, their bodies come out, so they're made to expand and go in a lot. But if you're a squid or a jellyfish or something like that, you can take the squeezing because it doesn't matter to you as much. You're spongy type, right? But also, most fish and type creatures at the bottom have either hard exoskeletons, like lobsters and stuff like that, or crabs, or they've got very hard out. They're very bony, very, very bony, because the bones help, flesh is nice, but it squishes, and you need a hard exterior to deal with all the pressure, all that thousands of feet of water above you. Okay? So and water is very much more dense than air, so that pressure gets really, really much, it gets to be a lot really fast, is a better way of saying it. And that becomes rho G H, or they use D. I'm sorry, D, they use D. Okay. Rho, of course, is the weight density. Yeah, it's the weight density. Mass density. That G is there, tells me it's mass density. Mass density. And then the D is the depth that you're down. So the further you go in a liquid, you start out with an initial pressure, atmospheric right here. And the further down you go, rho G D defines how much pressure you have. And that's a pretty straightforward calculation. Now, one thing that's interesting about pressures, one thing we need to talk about here is what if all right, so I've got a container like this. Here's a bunch of water, water everywhere. Not a drop to drink. Only if it's salt water, right? Or you have to stuff in. All right. Question. Right here and right here. P1 versus P2. Is P1 greater than P2? P1 less than P2? Or is P1 equal to P2? Is pressure 1 equal to pressure 2? Pressure 1 less than pressure 2? Pressure 1 greater than pressure 2? Mull that over for a minute, please, and I will wait. Mulling? Hopefully your mulling is going well. Keep mulling. Well, which one is it? Let's see if Chloe knows. Chloe, you've been a good cat staying here with me. Which one is it, girl? Which one is it? Is it this one? This one? Or that one? Chloe, you're right. It's the last one. Yay, Chloe. She's such a smart kitty. All right, there you go, girl. Good job. She's right. Pressure 1 equals pressure 2. Does it matter how wide or narrow it is above them? No, does it? It's a lot wider. All that matters is depth.